Adiabatic process. In an adiabatic process, in an ideal gas, no heat is added. At each step, dq equals 0 and dw by equals pdv. By the first law, du equals dq minus dw by, so we set dq equals 0 and dw by equals pdv to get du equals minus pdv. Since U changes at each step, so does the temperature T. In an adiabatic expansion, the gas does positive work and loses energy, and hence decreases in temperature or cools down. In an adiabatic compression, positive work is done on the gas, so it increases in temperature and heats up. Now for any step, du equals ncv dt. So we may substitute for du, and from the ideal gas law, PV equals nRT, so P equals nRT divided by V, which we may substitute for P. So from du equals minus pdv, we get, after performing the substitutions, ncv dt equals minus nRT dv divided by V. Divide through by n and by t. Now from Cp equals Cv plus R, we have Cp minus Cv equals R, which we substitute for R. Then divide both sides by Cv to get dt divided by t equals minus Cp minus Cv divided by Cv times dv divided by V. Simplifying, and noting that Cp divided by Cv equals gamma, the equation becomes dt divided by t equals minus gamma minus 1 dv divided by V. Integrate both sides. So natural log ln of t equals minus gamma minus 1 log V plus a constant of integration. We rearrange to get log t plus gamma minus 1 log V equals a constant, and use a law of logs, which is log of x to the power y equals y log x. So log t plus log V to the power gamma minus 1 equals constant, and we use another law of logs, log of xy equals log x plus log y, to get log of t times V to the gamma minus 1 equals a constant. If log of t times V to the gamma minus 1 is constant, then so is t times V to the gamma minus 1 equal to a constant, a different constant. This is a useful relation between T and V for an adiabatic process. To find a relation between P and V that can be plotted on a PV diagram, we use the ideal gas law, PV equals nRT, to obtain T equals PV divided by nR, which we substitute for T to get PV divided by nR times V to the gamma minus 1 equals a constant. Since nR is constant for a fixed quantity of gas, we have PV times V to the gamma minus 1 equals a constant. Note that V times V to the power gamma minus 1 is equal to V to the power 1 times V to the power gamma minus 1, which is equal to V to the power 1 plus gamma minus 1, which is equal to V to the power gamma. This gives us the final result, which is PV to the power gamma is equal to a constant. Note that we now have an expression for P as a function of V. Thus, for the initial and final states in an adiabatic process, PI/VI to the power gamma is equal to PF/VF to the power gamma, and TI/VI to the power gamma minus 1 is equal to TF/VF to the power gamma minus 1. On a PV diagram, we see that the adiabat starts on one isotherm at Ti and ends on another isotherm at Tf.